So as part of this course on Introduction to Disease Modelling, I'm going to be talking about undertaking a cost-effectiveness analysis using our model. So the outline of the presentation is to firstly look at the approach to determining cost-effectiveness, to introduce you to QALYs and DALYs, to look at the cost-effectiveness plane and the incremental cost-effectiveness ratio. So the learning objectives, by the end of the session, you should be able to plot health benefit and increment in cost associated with different policy options on a cost-effectiveness plane. You should be able to determine which policy options should be compared, calculate an incremental cost-effectiveness ratio, ICER, to make those comparisons. And lastly, to determine what is the most cost-effective policy option for a given cost-effectiveness threshold. So this slide lays out the approach to determine cost-effectiveness. So firstly, number one, to identify the alternative health policies that we want to consider. Then number two, to measure and value the health outcomes of each of the policies, ideally using QALYs or DALYs. Number three, to determine the costs of the alternative policies. Number four, to compare costs and health outcomes for all of the policy options. Then number five, remove policies that are clearly inferior to at least one other policy, which we refer to as a policy being dominated or extendedly dominated. Number six is to calculate the incremental cost-effectiveness ratio, the ICER, for the remaining policies that are not dominated, starting with the least costly policy. And finally, number seven, compare the ICER to a cost-effectiveness threshold. So we'll go through these in steps. First of all, identifying the alternative policies. Now, when identifying the alternative policies, we should consider the fullest possible range of policy options, including combining interventions if relevant, and or delivering interventions in subsets of the population only. So having identified the alternative policies, we then want to measure and value health outcomes and determine the costs of alternative policies. So the measures of health outcome we're going to consider are QALYs and DALYs. First of all, though, we'll consider another health outcome, life years. So this is illustrated here on this slide. We have the lives of 7 people over the years 2015 to 2018 illustrated. You can see that when a person dies, the pink line ends. And so in the year 2015, for example, at the start, you can see that we had a total of 7 life years experienced because all of our 7 people were alive. 1 had died by 2016, and so therefore there were only 6 life years experienced in 2016, etc. So that's life years. And now we come on to quality adjusted life years, or QALYs. So now the pink lines of people living, you can see that they have different widths. And the width of the pink for any person alive represents the sort of quality of life of that person at that point, where the fully pink would represent the fact that they have a perfect quality of life. And the indicator of the quality of life at a given point in time is this thing called a utility, and these utilities are widely agreed values for people in a given health state. So you can see, for example, in 2016 now, there's only 5.5 QALYs experienced because person number 5 has a health utility during that year of only 0.5. So another way of thinking about this, though, is years of life lost. And when we're talking about years of life lost, we're referring to years of life lost up to a particular age that a person might have lived to. So in this example, I'm suggesting the age might be age 90, but this does vary according to the way in which this is done. So now we have the same, the person when they're alive is in pink, but after they've died, the line continues in black until the time when they would have reached age 90. So if we then count the black lines, and so in 2015 there were no years of life lost incurred, but in 2016 there was 2 years of life lost incurred because person 3 and person 5 had died, and both of them would still have been less than age 90 had they been alive. And then again, similarly to the qualities that we had, we can also take into account the level of disability that the person is living with when they were alive. And so now, again, during the life of a person while they're alive, the pink line is not necessarily covering the whole line. There's also some black within the line as well, representing disability lived with at that point in time. And so disability adjusted life years count the years of life lost due to the person having died, but also years of life lost due to disability being lived in those living. So now in 2016, there's 1.5 DALYs incurred, and that's because person 3 had already died, but they would have been aged less than 90 had they not died. And person 4 was living with a disability weight of 0.5, and so they incurred 0.5 DALYs during that year. So there's a total of 1.5 DALYs. And you can see in the grey box there something about these disability weights. So again, like with the utilities for qualities, these are widely agreed values. And again, 0 here would be perfect health. And the disability weight, for example, for moderate depression is 0.4. So these disability weights, the greater the value, the higher the disability. Whilst with the qualities, the higher utility, the closer to perfect quality of life. And this shows some other examples of disability weights. Severe epilepsy, 0.55, Parkinson's, 0.27, moderate angina, 0.08, metastatic cancer, 0.45, cocaine dependence, moderate at 0.48, and blindness at 0.19. And also on our simulated individuals, we not only want to calculate the DALYs or the QALYs for each year, but we want to know for each individual the cost incurred from health budgets. So at any one point in time, we consider the costs incurred by the healthcare system for each person, trying to make sure we take into account the entire costs that are in fact incurred. So the costs incurred at any point in time, the components might include, for example, testing for presence of infection, clinic attendance costs, which would involve working out what it takes to be able to lay on clinics, taking into account equipment, infrastructure, buildings, administration, etc. Drug costs, hospitalization costs, costs of monitoring, for example. So at this point, I'd also like to mention discounting. So dealing with costs and health effects that extend into the future. So the consequences of decisions taken today can last for a very long time into the future. It is recommended to discount both future costs and health benefits. So discounting makes current costs and benefits worth more than those occurring in the future. So you can see the formula to the right of what the present value is plotted on the graph for $100 in current value by years into the future. And you can see from that that the cost declines by an annual discount rate. The value declines by an annual discount rate of 3%, 0.03. So you can see how much the present value declines over time. So why do we discount future cost and benefit at typically 3% per year? Well, first of all, because current spending incurs an opportunity cost relative to delayed spending, because a monetary investment yields a real rate of return, and therefore there's a cost to spending money in the present. So for example, if we have £100 today that we invest with a nominal return of 10%, then in a year's time it will be worth £110. If inflation was 4%, this would result in a real return of £6 on every £100 invested. So current spending would incur an opportunity cost relative to delaying the spending and getting that real return. The other reason for discounting is because of time preference. Individuals and societies tend to prefer to consume a product or service now rather than delay that same consumption some time into the future. So now you know about DALYs and how we count costs, we can talk about what a cost effectiveness analysis is. And essentially, it's a means of maximizing population health. So a certain amount of resource spent on an effective intervention can avert loss of healthy life years, i.e. it can avert DALYs. We don't want DALYs, we want to reduce them as much as possible. Cost effectiveness analysis is about allocating resources to health interventions so that we incur overall as low a number of DALYs as possible across the population. An intervention that averts DALYs can be characterized by how much we have to pay to avert one DALY. And this is what we call the incremental cost effectiveness ratio. It shows the cost per DALY averted of having that intervention in place. So continuing with how we actually do this, how we determine cost effectiveness, number 4 then is that we compare the costs that we've ascertained and the health outcomes for all of the policy options. So let's look at an example. So let's imagine we're modeling, in an individual-based model, we're modeling introduction of a new form of long-acting injectable pre-exposure prophylaxis, PrEP, to prevent HIV. Now we've used our model. Let's say we've got 100,000 simulated individuals and we've scaled up our outputs to represent the population size of the country or the setting we're interested in. In this case, we're imagining 7 million adults aged 15 to 65 in 2024. And we've run our model with each of 3 possible policy options. And we've run it over 50 years and we've calculated costs and DALYs, taking into account discounting. So the first policy is that there's no long-acting PrEP introduction at all. The second policy in pink is that there is introduction of long-acting PrEP, but that's only in female sex workers, FSW. And then in red, we have an alternative policy, which is to introduce long-acting PrEP not only in female sex workers, but also in adolescent girls and young women, AGYW. And you can see the results from our model simulations, that we've got the total number of DALYs in the second column incurred per year, and then in the third column, the total cost incurred per year. Now, in this case, the DALYs, the disability that we're taking into account, is of people living with HIV and having current toxicity to an antiretroviral drug or HIV-related morbidity or of course DALYs are incurred if they die prematurely. Now, I said the costs are in the third column. The main components of the costs here that were accounted for are the costs of PrEP itself, the costs of HIV tests, of antiretroviral drugs, clinic visits, viral load tests, and clinical care for HIV-related morbidity. And remember, this is the costs incurred by each individual in the adult population, not just those with HIV or just those that are going to be having PrEP. So then we've added a fourth and fifth column. In the fourth column, we're showing the difference in DALYs compared with not introducing long-acting PrEP. So for the pink policy of having it available only in female sex workers, you can see that we have on average of 5,766 DALYs, less DALYs with the policy than without the policy. And you can see how that calculation was made in brackets there. Whilst with the policy in red, where it's also introduced in adolescent girls and young women, you can see that there's a greater number of DALYs averted. So the number of DALYs, the difference in the number of DALYs is minus 9,810. So both of the policies improve population health because the number of DALYs incurred when the policy is introduced is lower than it would be if the policy hadn't been introduced. So what about the costs? So in the final column here, we've got the costs. And you can see that for the pink policy of introducing it in sex workers, the overall costs in the whole population, including in people living with HIV, are actually lower than they were without introduction of PrEP, 14.9 million lower. Whilst with the red policy, with introduction in adolescent girls and young women as well, there is an increase in costs overall. So it's 4.1 million higher cost as a result of introducing the policy. So now we can plot our model outputs, the fourth and fifth columns that we saw there. And this is something called a cost effectiveness plane. So we're plotting the health benefit on the x-axis and the increment in costs compared with no introduction on the y-axis. And so on the origin, 0, 0 is, because that's what we want to compare with primarily, is the no LA PrEP introduction. And then in the red, you can see that there were nearly 10,000 DALYs averted per year, but there was a slight increase in cost. So that's above the line, the x-axis. Whilst with the pink policy, there were over 5,000 DALYs averted, but it was also a lower overall cost. So we'll come back to this example. So we're going to break off now to talk more generally about the cost effectiveness plane. So this is what you've just seen with the example where a number of different potential health policies are plotted on a graph with the x-axis being the DALYs averted and the y-axis being the increment in costs. Now the comparator, the policy on the origin, is often the current policy, but it might be the least costly policy, for example. But the inference that we're going to draw from this is not affected by which policy is plotted on the origin. Now, of course, there's four quadrants to a cost effectiveness plane, and these tend to be referred to by the northwest, northeast, southeast, and southwest quadrants of the plane. So in the northeast quadrant, for example, that's where, compared with the origin, we have policies which have incurred more cost, but have also averted more DALYs. In the southeast quadrant, we have policies which have averted more DALYs than the comparator policy on the origin, but they're actually cheaper as well and incurred less cost. In the northwest quadrant, we don't have any policies here in this example, but these would be policies which incur more cost and actually result in less population health. So these are policies we really wouldn't be interested in introducing. And then in the southwest quadrant, we've got policies that they resulted in lower population health, but they also resulted in less cost. So in some circumstances, as you'll see, we might consider these. So for infectious diseases, we just want to note that the DALYs considered should include DALYs in the whole population which is susceptible to the infection, not just those with the infection at baseline. Now I'm showing you DALYs here and DALYs averted, but we could also consider other measures of health gain such as QALYs or infections averted. And just to remind you about the costs, these should convey the full cost implications to the healthcare system of implementing the policy option. Now note that in this module, we're only talking about costs from a healthcare system perspective and not considering costs incurred by patients, but there are other approaches which do this. So coming back to our list of the approach to determine cost effectiveness, we're now on to number 5, which is to remove policies which are clearly inferior. So that means they're dominated or extendedly dominated. And we'll see what that means. Now, policy for which there is another policy which is both more effective and less costly is said to be dominated. So you can see here the arrows going from one policy to two other policies, both of which are more costly and result in less population health than the policy from which the arrows come from. And so those two policies are dominated by the policy from which the arrows come. So we would never consider those policies above the policy which was dominating them. So they're not further considered. So what about extended domination? So a policy for which a combination of two other policies is both more effective and less costly is said to be extendedly dominated. So if you consider policies 2 and 3 with the square and the triangle, if we could carry out a mix of policy 2 and policy 3, then the resulting policy would lie somewhere on the line joining 2 and 3. Now in the region of that line, coloured red here, the resulting policy would dominate the policy, policy number 1 with the star. That would then be dominated. So in this case, we say that the policy number 1 is extendedly dominated. And again, extendedly dominated policies are not further considered. Okay, so we've taken out our dominated and extendedly dominated policies. So in this example, we're left with two policies. Now, between the remaining policies, the starting point is the policy that incurs the least cost. So that's the triangle. Then we ask for the next least costly policy, the square, what is the cost per additional DALY averted? This is the slope of the line joining the policies, and this is what's called the incremental cost effectiveness ratio. So the incremental cost effectiveness ratio, the ISA, is the increment in cost divided by the health benefit. Now in this case, we're using DALYs, so the health benefit is measured in DALYs averted. So the incremental cost effectiveness ratio is the increment in cost divided by the DALYs averted. So if we draw the line between the two policies, the policy with a square results in 150 million greater costs, but results in 230,000 extra DALYs averted. So the incremental cost effectiveness ratio is 150 million divided by 230,000. So that comes to $652 in this instance per DALY averted. So that is our ISA, $652. Now, if there are more than two non-dominated policies, we calculate ISAs incrementally, starting from the least costly policy. Now, ISAs will then increase as we move across the policy options. And this line showing the ISAs between the policies incrementally is called the cost effectiveness frontier. So for the first two policies here, you see that the ISA is $200 due to it being 50 million increase in costs, but 250,000 extra DALYs averted. And then from the second policy to the higher policy, the ISA is $800 because it costs 100 million more, but incurs 125,000 less DALYs. So let's go back to our long-acting PrEP example. So the first thing we want to do is to order the policies from the lowest to the highest cost. So now we now have the pink policy at the top because that one was the one that incurred the lowest cost, a lower cost than not having PrEP introduced at all. So then we calculate the DALYs averted compared with the cheapest policy option. So we've added this as a fourth row here. So the policy in black, which is not to introduce long-acting PrEP, as we've said, is more expensive than introducing it in female sex workers and also averts less DALYs. So this policy is dominated and we don't want to consider that any further. So now we can work out the incremental cost effectiveness ratio between our two remaining policies which are not dominated or extendedly dominated. So the difference in cost is 19 million and the difference in DALYs averted is 4,044. So that gives an ISA of 4,698. Okay, so let's come now to the final part of the approach to determine cost effectiveness. This is to compare the ISAs that we've calculated to a cost effectiveness threshold. So how low does the cost of averting DALYs, how low does the ISA need to be for an intervention to be cost effective? Answering this question requires a cost effectiveness threshold, which reflects the value of resources. In other words, what else they could buy. The threshold represents the opportunity cost, the value of the alternative that is foregone by spending on this intervention. Now, for low-income countries in sub-Saharan Africa, a cost effectiveness threshold of no more than $500 is probably realistic, since many interventions offering health gains at this amount or less, so with lower ISAs, remain unfunded. In fact, in one example country, for example, the threshold currently used is $61. So assuming we have a predetermined cost effectiveness threshold that we're going to be using, then once we've calculated our ISAs, then if the ISA is greater than the cost effectiveness threshold, then it is not cost effective. If we adopt such an intervention, we think there's more health lost or foregone from the commitment of resources to that intervention than results from its provision. Whilst if the ISA is less than the cost effectiveness threshold, then we say that the health policy is cost effective. So if we return to our example, and I should stress that this example is just using notional data. These are not real model outputs, and so they don't actually reflect the cost effectiveness of long-acting PrEP, I should stress. They're just used as an example. So when we're comparing the addition of PrEP, so we're already sure that PrEP for female sex workers is preferable to not providing LA PrEP at all. But what about to the additional provision to adolescent girls and young women? Our ISA, if you recall, was over $4,000. So that is not cost effective based on the cost effectiveness threshold if we were using $500 per daily averted, for example. So the conclusion we would draw is that the PrEP, LA PrEP and female sex workers is the most cost effective policy. It produces health benefit and saves costs compared to LA PrEP not being introduced. And I'll just emphasize again, these results are for illustration only and don't reflect current understanding of cost effectiveness of long-acting PrEP. Now, one approach to help think about the cost effectiveness threshold is a graph like this, where we've graphed each bar is a possible intervention that a country might introduce as part of its healthcare provision. And the y-axis shows the ISA for the intervention. So the interventions which have the lowest ISA are the things that you would start off by making sure you provide. So the first bar there by the y-axis has a low ISA, and that's provided. Now the width of the bar is the total cost of implementing that intervention. So basically you implement that intervention and then you look for the intervention with the next lowest ISA, and then you implement that and you work out what's the total cost incurred so far. And then you keep going along like that with adding interventions with the next lowest ISA. So then at a certain point, as you're going along the x-axis from 0, you reach your total healthcare budget. And it's at that point, if you look up to the y-axis for the ISA for the intervention which has just been added, this gives you an indication of the cost effectiveness threshold. Now, the approach I described, whereby we take out the policies which are dominated and we find the cost effective frontier, might sound quite complicated. But there is a graphical approach to finding the most cost-effective policy. So what you do is plot all policies on your cost-effectiveness plane relative to the policy with the lowest cost on the origin. Then you draw a line from the origin to the policy to the right of it with the lowest slope. And then you do the same from this policy. And you continue until there's no remaining policy to the right. So consider this situation here where we have the cost effectiveness plane with various policies plotted. And as I said, on the origin, we've got the policy which results in the lowest cost. So then we would draw the line to the policy to the right with the lowest slope, which we've done here. And then from that policy, we've gone again to the policy to the right with the lowest slope. Well, there's only one policy to the right at that point, and so we join up with that policy. And then we can calculate the ISA for each of those slopes. Here then is another example. And another. And another. And you can see at the bottom of the slide that what we do is we calculate ISAs, and then the last policy for which the ISA is less than our cost effectiveness threshold is selected as the cost effective policy. So hopefully now you've at least gone some way to be able to plot health benefit and increment in cost associated with different policy options on a cost-effectiveness plane. You can determine which policy option should be compared. You can calculate an incremental cost-effectiveness ratio to make those comparisons. And then you can determine what is the cost-effective policy option for a given cost-effectiveness threshold.